Reinforced Concrete by Edward Godfrey. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading by Deborah Lynn. Reader's Note: this extract is the beginning of the text and contains the author's paper only. For soporific purposes, I retained the list of men whose discussion follows this extract. End of Reader's Note. American Society of Civil Engineers, instituted 1852. Transactions. Paper number 1169. Some Mooted Questions in Reinforced Concrete Design. Footnote A. By Edward Godfrey, M.A.M. SOC C.E. With discussion by Messrs. Joseph Wright, S. Bent Russell, J. R. Worcester, L. J. Mensch, Walter W. Clifford, J. C. Meem, George H. Myers, Edwin Thatcher, C. A. P. Turner, Paul Chapman, E. P. Goodrich, Alban H. Beyer, John C. Ostrop, Harry F. Porter, John Stephen Sewell, Sanford E. Thompson, and Edward Godfrey. Not many years ago, physicians had certain rules and practices by which they were guided as to when and where to bleed a patient in order to relieve or cure him. What of those rules and practices today? If they were logical, why have they been abandoned? It is the purpose of this paper to show that reinforced concrete engineers have certain rules and practices which are no more logical than those governing the bloodletting of former days. If the writer fails in this, by reason of the more weighty arguments on the other side of the questions he propounds, he will at least have brought out good reasons which will stand the test of logic for the rules and practices which he proposes to condemn, and which at the present time are quite lacking in the voluminous literature on this comparatively new subject. Destructive criticism has recently been decried in an editorial in an engineering journal. Some kinds of destructive criticism are of the highest benefit. When it succeeds in destroying error, it is reconstructive. No reform was ever accomplished without it, and no reformer ever existed who was not a destructive critic. If showing up errors and faults is destructive criticism, we cannot have too much of it. In fact, we cannot advance without it. If engineering practice is to be purged of its inconsistencies and absurdities, it will never be done by dwelling on its excellencies. Reinforced concrete engineering has fairly leaped into prominence and apparently into full growth, but it still wears some of its swaddling bands. Some of the garments which it borrowed from sister forms of construction in its short infancy still cling to it, and while these were perhaps the best makeshifts under the circumstances, they fit badly and should be discarded. It is some of these misfits and absurdities which the writer would like to bring prominently before the engineering profession. Illustration Figure 1. The first point to which attention is called is illustrated in Figure 1. It concerns sharp bends in reinforcing rods in concrete. Figure 1 shows a reinforced concrete design, one held out in nearly all books on the subject as a model. The reinforcing rod is bent up at a sharp angle, and then may or may not be bent again and run parallel with the top of the beam. At the bend is a condition which resembles that of a hog chain or truss rod around a queen post. The reinforcing rod is the hog chain or the truss rod. Where is the queen post? Suppose this rod has a section of 1 square inch and an inclination of 60 degrees with the horizontal, and that its unit stress is 16,000 pounds per square inch. The forces A and B are then 16,000 pounds. The force C must also be 16,000 pounds. What is to take this force C of 16,000 pounds? there is nothing but concrete. At 500 pounds per square inch, this force would require an area of 32 square inches. Will some advocate of this type of design please state where this area can be found? It must of necessity be in contact with the rod, and for structural reasons, because of the lack of stiffness in the rod, it would have to be close to the point of bend. If analogy to the queen post fails so completely because of the almost complete absence of the post, why should not this borrowed garment be discarded? If this same rod be given a gentle curve of a radius 20 or 30 times the diameter of the rod, the side unit pressure will be from 1/20th to 1/30th of the unit stress on the steel. This being the case, and being a simple principle of mechanics which ought to be thoroughly understood, it is astounding that engineers should perpetrate the gross error of making a sharp bend in a reinforcing rod under stress. The second point to which attention is called may also be illustrated by Figure 1. The rod marked 3 is also like the truss rod of a queen post truss in appearance, because it ends over the support and has the same shape. But the analogy ends with appearance, for the function of a truss rod in a queen post truss is not performed by such a reinforcing rod in concrete, for other reasons than the absence of a post. The truss rod receives its stress by a suitable connection at the end of the rod and over the support of the beam. The reinforcing rod in this standard beam ends abruptly at the very point where it is due to receive an important element of strength, an element which would add enormously to the strength and safety of many a beam if it could be introduced. Of course, a reinforcing rod in a concrete beam receives its stress by increments imparted by the grip of the concrete, but these increments can only be imparted where the tendency of the concrete is to stretch. This tendency is greatest near the bottom of the beam, and when the rod is bent up to the top of the beam, it is taken out of the region where the concrete has the greatest tendency to stretch. The function of this rod as reinforcement of the bottom flange of the beam is interfered with by bending it up in this manner, as the beam is left without bottom flange reinforcement, as far as that rod is concerned, from the point of bend to the support. It is true that there is a shear or a diagonal tension in the beam, and the diagonal portion of the rod is apparently in a position to take this tension. This is just such a force as the truss rod in a queen post truss must take. Is this reinforcing rod equipped to perform this office? The beam is apt to fail in the line AB. In fact, it is apt to crack from shrinkage on this or almost any other line, and to leave the strength dependent on the reinforcing steel. Suppose such a crack should occur, the entire strength of the beam would be dependent on the grip of the short end of rod 3 to the right of the line AB. The grip of this short piece of rod is so small and precarious, considering the important duty it has to perform, that it is astounding that designers, having any care for the permanence of their structures, should consider for an instant such features of design, much less incorporate them in a building in which life and property depend on them. The third point to which attention is called is the feature of design just mentioned in connection with the bent-up rod. It concerns the anchorage of rods by the embedment of a few inches of their length in concrete. This most flagrant violation of common sense has its most conspicuous example in large engineering works, where of all places better judgment should prevail. Many retaining walls have been built and described in engineering journals, in papers before engineering societies of the highest order, and in books enjoying the greatest reputation, which have as an essential feature a great number of rods which cannot possibly develop their strength and might as well be of much smaller dimensions. These rods are the vertical and horizontal rods in the counterfort of the retaining wall, shown at A in Figure 2. This retaining wall consists of a front curtain wall and a horizontal slab, joined at intervals by ribs or counterforts. The manifest and only function of the rib or counterfort is to tie together the curtain wall and the horizontal slab. That it is or should be of concrete is because the steel rods which it contains need protection. It is clear that failure of the retaining wall could occur by rupture through the section AB or through BC. It is also clear that apart from the cracking of the concrete of the rib, the only thing which would produce this rupture is the pulling out of the short ends of these reinforcing rods. Writers treat the triangle ABC as a beam, but there is absolutely no analogy between this triangle and a beam. Designers seem to think that these rods take the place of so-called shear rods in a beam, and that the inclined rods are equivalent to the rods in a tension flange of a beam. It is hard to understand by what process of reasoning such results can be attained. Any clear analysis leading to these conclusions would certainly be a valuable contribution to the literature on the subject. It is scarcely possible, however, that such analysis will be brought forward, for it is the apparent policy of the reinforced concrete analyst to jump into the middle of his proposition without the encumbrance of a premise. There is positively no evading the fact that this wall could fail, as stated, by rupture along either AB or BC. It can be stated just as positively that a set of rods running from the front wall to the horizontal slab and anchored into each in such a manner as would be adopted were these slabs suspended on the rods is the only rational and the only efficient design possible. This design is illustrated at B in Figure 2. Illustration, Figure 2. The fourth point concerns shear in steel rods embedded in concrete. For decades, specifications for steel bridges have gravely given a unit shear to be allowed on bridge pins, and every bridge engineer knows or ought to know that if a bridge pin is properly proportioned for bending and bearing, there is no possibility of its being weak from shear. The centers of bearings cannot be brought close enough together to reduce the size of the pin to where its shear need be considered, because of the width required for bearing on the parts. Concrete is about 1/30th as strong as steel in bearing. There is, therefore, somewhat less than 1/30th of a reason for specifying any shear on steel rods embedded in concrete. The gravity of the situation is not so much the serious manner in which this unit of shear in steel is written in specifications and building codes for reinforced concrete work. It does not mean anything in specifications for steel work because it is ignored, but it is apparent when designers soberly use these absurd units and proportion shear rods accordingly. Many designers actually proportion shear rods for shear in the steel at units of 10,000 or 12,000 pounds per square inch, and the blame for this dangerous practice can be laid directly to the literature on reinforced concrete. Shear rods are given as standard features in the design of reinforced concrete beams. In the joint report of the committee of the various engineering societies, a method for proportioning shear members is given. The stress, or shear per shear member, is the longitudinal shear which would occur in the space from member to member. No hint is given as to whether these bars are in shear or tension. In fact, either would be absurd and impossible without greatly overstressing some other part. This is just a sample of the state of the literature on this important subject. Shear bars will be taken up more fully in subsequent paragraphs. The fifth point concerns vertical stirrups in a beam. These stirrups are conspicuous features in the designs of reinforcing concrete beams. Explanations of how they act are conspicuous in the literature on reinforced concrete by its total absence. By stirrups are meant the so-called shear rods strung along a reinforcing rod. They are usually U-shaped and looped around the rod. It is common practice to count these stirrups in the shear, taking the horizontal shear in a beam. In a plate girder, the rivets connecting the flange to the web take the horizontal shear, or the increment to the flange stress. Compare two 3/4-inch rivets tightly driven into holes in a steel angle, with a loose vertical rod 3/4 of an inch in diameter looped around a reinforcing rod in a concrete beam, and a correct comparison of methods of design in steel and reinforced concrete, as they are commonly practiced, is obtained. These stirrups can take but little hold on the reinforcing rods, and this must be through the medium of the concrete, and they can take but little shear. Some writers, however, hold the opinion that the stirrups are in tension and not in shear, and some are bold enough to compare them with the vertical tension members of a howe truss. Imagine a howe truss with the vertical tension members looped around the bottom cord and run up to the top cord without any connection, or hooked over the top cord. Then compare such a truss with one in which the end of the rod is upset, and receives a nut and large washer bearing solidly against the cord. This gives a comparison of methods of design in wood and reinforced concrete, as they are commonly practiced. Anchorage or grip in the concrete is all that can be counted on in any event to take up the tension of these stirrups, but it requires an embedment of from 30 to 50 diameters of a rod to develop its full strength. Take 30 to 50 diameters from the floating end of these shear members, and in some cases nothing or less than nothing will be left. In any case, the point at which the shear member or stirrup is good for its full value is far short of the centroid of compression of the beam where it should be. In most cases it will be nearer the bottom of the beam. In a howe truss, the vertical tension members having their end connections near the bottom cord would be equivalent to these shear members. The sixth point concerns the division of stress into shear members. Briefly stated, the common method is to assume each shear member as taking the horizontal shear occurring in the space from member to member. As already stated, this is absurd. If stirrups could take shear, this method would give the shear per stirrup, but even advocates of this method acknowledge that they cannot. To apply the common analogy of a truss, each shear member would represent a tension web member in the truss, and each would have to take all the shear occurring in a section through it. If, for example, shear members were spaced half the depth of a beam apart, each would take half the shear by the common method. If shear members take vertical shear, or if they take tension, what is between the two members to take the other half of the shear? There is nothing in the beam but concrete and the tension rod between the two shear members. If the concrete can take the shear, why use steel members? It is not conceivable that an engineer should seriously consider a tension rod in a reinforced concrete beam as carrying the shear from stirrup to stirrup. The logical deduction from the proposition that shear rods take tension is that the tension rods must take shear, and that they must take the full shear of the beam and not only a part of it. For these shear rods are looped around or attached to the tension rods, and since tension in the shear rods would logically be imparted through the medium of this attachment, there is no escaping the conclusion that a large vertical force, the shear of the beam, must pass through the tension rod. If the shear member really relieves the concrete of the shear, it must take it all. If, as would be allowable, the shear rods take but a part of the shear, leaving the concrete to take the remainder, that carried by the rods should not be divided again, as is recommended by the common method. Bulletin number 29 of the University of Illinois Experiment Station shows by numerous experiments and reiterates again and again that shear rods do not act until the beam has cracked and partly failed. This being the case, a shear rod is an illogical element of design. Any element of a structure which cannot act until failure has started is not a proper element of design. In a steel structure, A bent plate which would straighten out under a small stress and then resist final rupture would be a menace to the rigidity and stability of the structure. This is exactly analogous to shear rods, which cannot act until failure has begun. When the man who tears down by criticism fails to point out the way to build up, he is a destructive critic. If under the circumstances designing with shear rods had the virtue of being the best thing to do with the steel and concrete disposed in a beam, as far as experience and logic in their present state could decide, nothing would be gained by simply criticizing this method of design. But logic and tests have shown a far simpler, more effective, and more economical means of disposing of the steel in a reinforced concrete beam. In shallow beams there is little need of provision for taking shear by any other means than the concrete itself. The writer has seen a reinforced slab support a very heavy load by simple friction, for the slab was cracked close to the supports. In slabs, shear is seldom provided for in the steel reinforcement. It is only when beams begin to have a depth approximating 1/10 of the span that the shear in the concrete becomes excessive and provision is necessary in the steel reinforcement. Years ago the writer recommended that in such beams some of the rods be curved up toward the ends of the span and anchored over the support. Such reinforcement completely relieves the concrete of all shearing stress, for the stress in the rod will have a vertical component equal to the shear. The concrete will rest in the rod as a saddle, and the rod will be like the cable of a suspension span. The concrete should be in separate blocks with vertical joints, and still the load would be carried safely. By end anchorage is not meant an inch or two of embedment in concrete, for an iron vise would not hold a rod for its full value by such means. Neither does it mean a hook on the end of the rod. A threaded end with a bearing washer and a nut and a lock nut to hold the washer in place is about the only effective means, and it is simple and cheap. Nothing is as good for this purpose as plain round rods, for no other shape affords the same simple and effective means of end connection. In a line of beams end to end, the rods may be extended into the next beam, and there act to take the top flange tension, while at the same time finding anchorage for the principal beam stress. The simplicity of this design is shown still further by the absence of a large number of little pieces in a beam box, as these must be held in their proper places, and as they interfere with the pouring of the concrete. It is surprising that this simple and unpatented method of design has not met with more favor, and has scarcely been used even in tests. Some time ago the writer was asked by the head of an engineering department of a college for some ideas for the students to work up for theses, and suggested that they test beams of this sort. He was met by the astounding and fatuous reply that such would not be reinforced concrete beams. They would certainly be concrete beams, and just as certainly be reinforced. Bulletin 29 of the University of Illinois Experiment Station contains a record of tests of reinforced concrete beams of this sort. They failed by the crushing of the concrete or by failure in the steel rods, and nearly all the cracks were in the middle third of the beams, whereas beams rich in shear rods cracked principally in the end thirds, that is, in the neighborhood of the shear rods. The former failures are ideal, and are easier to provide against. A crack in a beam near the middle of the span is of little consequence, whereas one near the support is a menace to safety. The seventh point of common practice to which attention is called is the manner in which bending moments in so-called continuous beams are juggled to reduce them to what the designer would like to have them. This has come to be almost a matter of taste, and is done with as much precision or reason as geologists guess at the age of a fossil in millions of years. If a line of continuous beams be loaded uniformly, the maximum moments are negative and are over the supports. Who ever heard of a line of beams in which the reinforcement over the supports was double that at mid-spans? The end support of such a line of beams cannot be said to be fixed, but is simply supported. Hence the end beam would have a negative bending moment over next to the last support equal to that of a simple span. Who ever heard of a beam being reinforced for this? The common practice is to make a reduction in the bending moment at the middle of the span to about that of a line of continuous beams, regardless of the fact that they may not be continuous or even contiguous, and in spite of the fact that the loading of only one gives quite different results, and may give results approaching those of a simple beam. If the beams be designed as simple beams, taking the clear distance between supports as the span and not the centers of bearings or the centers of supports, and if a reasonable top reinforcement be used over these supports to prevent cracks, every requirement of good engineering is met. Under extreme conditions, such construction might be heavily stressed in the steel over the supports. It might even be overstressed in this steel. But what could happen? Not failure, for the beams are capable of carrying their load individually, and even if the rods over the supports were severed, a thing impossible because they cannot stretch out sufficiently, the beams would stand. Continuous beam calculations have no place whatever in designing stringers of a steel bridge, though the end connections will often take a very large moment, and if calculated as continuous will be bound to be strained to a very much larger moment. Who ever heard of a failure because of continuous beam action in the stringers of a bridge? Why cannot reinforced concrete engineering be placed on the same sound footing as structural steel engineering? The 8th point concerns the spacing of rods in a reinforced concrete beam. It is common to see rods bunched in the bottom of such a beam, with no regard whatever for the ability of the concrete to grip the steel, or to carry the horizontal shear incident to their stress to the upper part of the beam. As an illustration of the logic and analysis applied in discussing the subject of reinforced concrete, one well-known authority, on the premise that the unit of adhesion to rod and of shear are equal, derives a rule for the spacing of rods. His reasoning is so false, and his rule is so far from being correct, that 2/3 would have to be added to the width of beam in order to make it correct. An error of 66% may seem trifling to some minds where reinforced concrete is considered, but errors of 1/10 this amount in steel design would be cause for serious concern. It is reasoning of the most elementary kind which shows that if shear and adhesion are equal, the width of a reinforced concrete beam should be equal to the sum of the peripheries of all reinforcing rods gripped by the concrete. The width of the beam is the measure of the shearing area above the rods, taking the horizontal shear to the top of the beam, and the peripheries of the rods are the measure of the gripping or adhesion area. Analysis which examines a beam to determine whether or not there is sufficient concrete to grip the steel and to carry the shear is about at the vanishing point in nearly all books on the subject. Such misleading analysis as that just cited is worse than nothing. The 9th point concerns the T-beam. Excessively elaborate formulas are worked out for the T-beam, and haphazard guesses are made as to how much of the floor slab may be considered in the compression flange. If a fraction of this mental energy were directed toward a logical analysis of the shear and gripping value of the stem of the T-beam, it would be found that when the stem is given its proper width, little if any of the floor slab will have to be counted in the compression flange, for the width of concrete which will grip the rods properly will take the compression incident to their stress. The 10th point concerns elaborate theories and formulas for beams and slabs. Formulas are commonly given with 25 or 30 constants and variables to be estimated and guessed at, and are based on assumptions which are inaccurate and untrue. One of these assumptions is that the concrete is initially unstressed. This is quite out of reason, for the shrinkage of the concrete on hardening puts stress in both concrete and steel. One of the coefficients of the formulas is that of the elasticity of the concrete. No more variable property of concrete is known than its coefficient of elasticity, which may vary from 1,000,000 to 5,000,000 or 6,000,000. It varies with the intensity of stress, with the kind of aggregate used, with the amount of water used in mixing, and with the atmospheric condition during setting. The unknown coefficient of elasticity of concrete and the non-existent condition of no initial stress vitiate entirely formulas supported by these two props. Here again destructive criticism would be vicious if these mathematical gymnasts were giving the best or only solution which present knowledge could produce, or if the critic did not point out a substitute. The substitute is so simple of application, in such agreement with experiments, and so logical in its derivation, that it is surprising that it has not been generally adopted. The neutral axis of reinforced concrete beams under safe loads is near the middle of the depth of the beams. If in all cases it be taken at the middle of the depth of the concrete beam, and if variation of intensity of stress in the concrete be taken as uniform from this neutral axis up, the formula for the resisting moment of a reinforced concrete beam becomes extremely simple and no more complex than that for a rectangular wooden beam. The 11th point concerns complex formulas for chimneys. It is a simple matter to find the tensile stress in that part of a plain concrete chimney between two radii on the windward side. If in this space there is inserted a rod which is capable of taking that tension at a proper unit, the safety of the chimney is assured as far as that tensile stress is concerned. Why should frightfully complex formulas be proposed which bring in the unknowable modulus of elasticity of concrete, and can only be solved by stages or dependence on the calculations of someone else? The 12th point concerns deflection calculations. As is well known, deflection does not play much of a part in the design of beams. Sometimes, however, the passing requirement of a certain floor construction is the amount of deflection under a given load. Professor Gaetano Lanza has given some data on recorded deflections of reinforced concrete beams. Footnote B. He has also worked out the theoretical deflections on various assumptions. An attempt to reconcile the observed deflections with one of several methods of calculating stresses led him to the conclusion that the observations made thus far are not sufficient to furnish the means for determining the actual distribution of the stresses, and hence for the deduction of reliable formula for the computation of the direct stresses, shearing stresses, diagonal stresses, deflections, position of the neutral axis, etc., under a given load. Professor Lanza might have gone further, and said that the observations made thus far are sufficient to show the hopelessness of deriving a formula that will predict accurately the deflection of a reinforced concrete beam. The wide variation shown by two beam tests cited by him, in which the beams were identical, is in itself proof of this. Taking the data of these tests and working out the modulus of elasticity from the recorded deflections, as though the beams were of plain concrete, values are found for this modulus which are not out of agreement with the value of that variable modulus as determined by other means. Therefore, if the beams be considered as plain concrete beams, and an average value be assumed for the modulus or coefficient of elasticity, a deflection may be found by a simple calculation, which is an average of that which may be expected. Here again simple theory is better than complex, because of the ease with which it may be applied, and because it gives results which are just as reliable. The 13th point concerns the elastic theory as applied to a reinforced concrete arch. This theory treats a reinforced concrete arch as a spring. In order to justify its use, the arch or spring is considered as having fixed ends. The results obtained by the intricate methods of the elastic theory and the simple method of the equilibrium polygon are too nearly identical to justify the former when the arch is taken as hinged at the ends. The assumption of fixed ends in an arch is a most extravagant one, because it means that the abutments must be rigid, that is, capable of taking bending moments. Rigidity in an abutment is only effected by a large increase in bulk, whereas strength in an arch ring is greatly augmented by the addition of a few inches to its thickness. By the elastic theory, the arch ring does not appear to need as much strength as by the other method, but additional stability is needed in the abutments in order to take the bending moments. This latter feature is not dwelt on by the elastic theorists. In the ordinary arch, the criterion by which the size of abutment is gauged is the location of the line of pressure. It is difficult and expensive to obtain depth enough in the base of the abutment to keep this line within the middle third, when only the thrust of the arch is considered. If, in addition to the thrust, there is a bending moment which, from any conditions of loading, further displaces the line of pressure toward the critical edge, the difficulty and expense are increased. It cannot be gainsaid that a few cubic yards of concrete added to the ring of an arch will go much further toward strengthening the arch than the same amount of concrete added to the two abutments. In reinforced concrete there are ample grounds for the contention that the carrying out of a nice theory based on nice assumptions and the exact determination of ideal stresses is of far less importance than the building of a structure which is in every way capable of performing its function. There are more than ample grounds for the contention that the ideal stresses worked out for a reinforced concrete structure are far from realization in this far from ideal material. Apart from the objection that the elastic theory, instead of showing economy by cutting down the thickness of the arch ring, would show the very opposite if fully carried out, there are objections of greater weight, objections which strike at the very foundation of the theory as applied to reinforced concrete. In the elastic theory, as in the intricate beam theory commonly used, there is the assumption of an initial unstressed condition of the materials. This is not true of a beam and is still further from the truth in the case of an arch. Besides shrinkage of the concrete, which always produces unknown initial stresses, there is a still more potent cause of initial stress, namely the settlement of the arch when the forms are removed. If the initial stresses are unknown, ideal determinations of stresses can have little meaning. The elastic theory stands or falls according as one is able or unable to calculate accurately the deflection of a reinforced concrete beam, and it is an impossibility to calculate this deflection even approximately. The tests cited by Professor Lanza show the utter disagreement in the matter of deflections. Of those tested, 2 beams, which were identical, showed results almost 100% apart. A theory grounded on such a shifting foundation does not deserve serious consideration. Professor Lanza's conclusions, quoted under the 12th point, have special meaning and force when applied to a reinforced concrete arch. The actual distribution of the stresses cannot possibly be determined, and complex cloaks of arithmetic cannot cover this fact. The elastic theory, far from being a reliable formula, is false and misleading in the extreme. The 14th point refers to temperature calculations in a reinforced concrete arch. These calculations have no meaning whatever. To give the grounds for this assertion would be to reiterate much of what has been said under the subject of the elastic arch. If the unstressed shape of an arch cannot be determined because of the unknown effect of shrinkage and settlement, it is a waste of time to work out a slightly different unstressed shape due to temperature variation, and it is a further waste of time to work out the supposed stresses resulting from deflecting that arch back to its actual shape. If no other method of finding the approximate stresses in an arch existed, the elastic theory might be classed as the best available, but this is not the case. There is a method which is both simple and reliable. Accuracy is not claimed for it, and hence it is in accord with the more or less uncertain materials dealt with. Complete safety, however, is assured, for it treats the arch as a series of blocks, and the cementing of these blocks into one mass cannot weaken the arch. Reinforcement can be proportioned in the same manner as for chimneys, by finding the tension exerted to pull these blocks apart, and then providing steel to take that tension. The 15th point concerns steel in compression in reinforced concrete columns or beams. It is common practice, and it is recommended in the most pretentious works on the subject, to include in the strength of a concrete column slender longitudinal rods embedded in the concrete. To quote from one of these works, "The compressive resistance of a hooped member exceeds the sum of the following three elements: 1. The compressive resistance of the concrete without reinforcement. 2. The compressive resistance of the longitudinal rods stressed to their elastic limit. 3. The compressive resistance which would have been produced by the imaginary longitudinals at the elastic limit of the hooping metal, the volume of the imaginary longitudinals being taken as 2.4 times that of the hooping metal." This does not stand the test either of theory or practice. In fact, it is far from being true. Its departure from the truth is great enough and of serious enough moment to explain some of the worst accidents in the history of reinforced concrete. It is a nice theoretical conception that the steel and the concrete act together to take the compression, and that each is accommodating enough to take just as much of the load as will stress it to just the right unit. Here again initial stress plays an important part. The shrinkage of the concrete tends to put the rods in compression. The load adds more compression on the slender rods, and they buckle, because of the lack of any adequate stiffening, long before the theorist's ultimate load is reached. There is no theoretical or practical consideration which would bring in the strength of the hoops after the strength of the concrete between them has been counted. All the compression of a column must, of necessity, go through the disc of concrete between the two hoops and the longitudinal steel. No additional strength in the hoops can affect the strength of this disc with a given spacing of the hoops. It is true that shorter discs will have more strength, but this is a matter of the spacing of the hoops and not of their sectional area, as the above quotation would make it appear. Besides being false theoretically, this method of investing phantom columns with real strength is woefully lacking in practical foundation. Even the assumption of reinforcing value to the longitudinal steel rods is not at all borne out in tests. Designers add enormously to the calculated strength of concrete columns when they insert some longitudinal rods. It appears to be the rule that real columns are weakened by the very means which these designers invest with reinforcing properties. Whether or not it is the rule, the mere fact that many tests have shown these so-called reinforced concrete columns to be weaker than similar plain concrete columns is amply sufficient to condemn the practice of assuming strength which may not exist. Of all parts of a building, the columns are the most vital. The failure of one column will, in all probability, carry with it many others stronger than itself, whereas a weak and failing slab or beam does not put an extra load and shock on the neighboring parts of a structure. In Bulletin No. 10 of the University of Illinois Experiment Station, footnote C, a plain concrete column, 9 by 9 inches by 12 feet, stood an ultimate crushing load of 2,004 pounds per square inch. Column 2, identical in size and having 4 5/8-inch rods embedded in the concrete, stood 1,557 pounds per square inch. So much for longitudinal rods without hoops. This is not an isolated case, but appears to be the rule, and yet, in reading the literature on the subject, one would be led to believe that longitudinal steel rods in a plain concrete column add greatly to the strength of the column. A paper by Mr. M.O. Withy before the American Society for Testing Materials in 1909 gave the results of some tests on concrete steel and plain concrete columns. The term concrete steel is used because this particular combination is not reinforced concrete. One group of columns, namely W1 to W3, 10½ inches in diameter, 102 inches long, and circular in shape, stood an average ultimate load of 2,600 pounds per square inch. These columns were of plain concrete. Another group, namely E1 to E3, were octagonal in shape with a short diameter, 12 inches, their length being 120 inches. These columns contained 9 longitudinal rods, 5/8 inch in diameter, and 1/4 inch steel rings every foot. They stood an ultimate load averaging 2,438 pounds per square inch. This is less than the column with no steel and with practically the same ratio of slenderness. In some tests on columns made by the Department of Buildings of Minneapolis, Minnesota, footnote D, Test A was a 9 by 9 inch column, 9 feet 6 inches long, with 10 longitudinal round rods, 1/2 inch in diameter, and 1½ inch by 3/16 inch circular bands having 2 1/2 inch rivets in the splice, spaced 4 inches apart, the circles being 7 inches in diameter. It carried an ultimate load of 130,000 pounds, which is much less than half the compressive resistance of a hooped member, worked out according to the authoritative quotation before given. Another similar column stood a little more than half that compressive resistance. 5 of the 17 tests on the concrete steel columns made at Minneapolis stood less than the plain concrete columns. So much for the longitudinal rods, and for hoops, which are not close enough to stiffen the rods, and yet in reading the literature on the subject any one would be led to believe that longitudinal rods and hoops add enormously to the strength of a concrete column. The 16th indictment against common practice is in reference to flat slabs supported on 4 sides. Grasshoff's formula for flat plates has no application to reinforced concrete slabs, because it is derived for a material strong in all directions and equally stressed. The strength of concrete in tension is almost nil, at least it should be so considered. Poisson's ratio, so prominent in Grasshoff's formula, has no meaning whatever in steel reinforcement for a slab, because each rod must take tension only, and instead of a material equally stressed in all directions, there are generally sets of independent rods in only 2 directions. In a solution of the problem given by a high English authority, the slab is assumed to have a bending moment of equal intensity along its diagonal. It is quite absurd to assume an intensity of bending clear into the corner of a slab, and on the very support equal to that at its center. A method published by the writer some years ago has not been challenged. By this method strips are taken across the slab, and the moment in them is found, considering the limitations of the several strips in deflection imposed by those running at right angles therewith. This method shows, as tests demonstrate, that when the slab is oblong, reinforcement in the long direction rapidly diminishes in usefulness. When the ratio is 1 to 1½ reinforcement in the long direction is needless, since that in the short direction is required to take its full amount. In this way, French and other regulations give false results and fail to work out. If the writer is wrong in any or all of the foregoing points, it should be easy to disprove his assertions. It would be better to do this than to ridicule or ignore them, and it would be even better than to issue reports signed by authorities which commend the practices herein condemned. Footnotes. Footnote A, presented at the meeting of March 16, 1910. Footnote B, stresses in reinforced concrete beams. Journal, American Society of Mechanical Engineers, mid-October 1909. Footnote C, page 14, column 8. Footnote D, Engineering News, December 3, 1908. End of selection.